All right. Welcome to the 11th lecture in this calculus series. So today we're going to talk about inverse functions and just what's the story with inverse functions and derivatives. And then we'll get into some very important specific inverse functions from trigonometry, which I'm sure you can imagine will have interesting derivatives. So let's go ahead and get started. We'll call this 2.6 derivatives of inverse functions. Okay. So let's just start with the facts here. So let's let f be a function whose domain is some interval I. Okay, so f is a function on an interval I. Now, if f has an inverse function, okay, on the interval I, then the following statements are true. So if f has an inverse function, then the following are true. Okay, we'll just kind of state these here. So first thing that's true is that if f is continuous, then its inverse is continuous. Well, that's nice, right? And I guess that's probably to be expected. I mean, we're not going to prove that, but that's probably not a stretch. F being continuous implies that f inverse is continuous. Okay. Now, given that, we have also that if f is differentiable, so if f is differentiable at c, some point c, and f prime of c is non-zero, right? So a non-zero derivative, then f inverse is differentiable at f of c, right? Okay, so that's good too. Okay, so the idea, now keep in mind the idea here, right? So you basically two domains here, right? So you've got some point C, right? And it maps over to f of c. Okay, so if f is differentiable at c, right, meaning over here f is differentiable, and if that derivative is non-zero, then the inverse function is differentiable at f of c. Okay. All right. So basically, if you have a function f, if f is differentiable, then it's likely that its inverse, if it has an inverse, is differentiable as well. And it's likely that the derivative is going to follow the rules of differentiability. It's going to inherit that from f. Another way to say it. Okay. All right. So that's kind of the big picture, right? So basically, if f has an inverse, then f inverse is almost always differentiable, and it works in the way that you would expect. If I can differentiate f at c, then I'm likely to be able to differentiate f inverse at f of c, right? Very good. As you would like it. Then kind of sometimes things work out. Here's a theorem that's a little tricky to get your head around at first, but we'll do some examples. So let f be a function that is differentiable on an interval I. Okay. Now, if f has an inverse function, okay, if f has an inverse function g, we'll just call it g, then g is differentiable okay, at any x for which f prime of g of x is non-zero. Okay, so what is this? So this is f prime of f inverse of x. Maybe it's even easier to use the f notation. But so let f be a function that is differentiable on an interval I. Okay, now if f has an inverse function g, then g is differentiable at any x for which f prime of f inverse is non-zero. Okay, and moreover, okay, the value of that derivative, the value of the derivative of the inverse function is equal to 1 over f prime of g of x, provided, of course, wherever f prime of g of x is non-zero. Naturally, because you can't divide by 0 here. Okay, so that's kind of a mouthful there. So if f is a function, it's differentiable. It's a differentiable function. F has an inverse function, g. G is also differentiable, and it's differentiable at any x where the derivative evaluated at the inverse is non-zero. And specifically, the derivative of the inverse g is equal to 1 over the derivative of f evaluated at the inverse. Okay, so let's do a concrete example. So this is the theorem. This is the theorem, the big theorem. Let's do an example. Okay, we're going to kind of flush this out with an example. So let's let f of x equal this polynomial, maybe 1/4 x cubed plus x minus 1. Okay, so that's our function f. Now, f has a derivative. We can calculate the derivative. And the derivative here would be 3/4 x squared plus 1. Okay, so that's our derivative. All right. Now let's look at like a specific point. So f of 2, for example. So f of 2 is equal to 1/4 times 2 cubed plus 2 minus 1. So when you do all of that math, you get like what, 8/4 plus 2 minus 1, you get 3. Okay, so f evaluated at the point x equals 2 is equal to 3. And so f has an inverse function. And so if f of 2 is equal to 3, right, then f inverse of 3 would be equal to 2, right? That's kind of the way inverses work, right? So f of 2 is 3, then f inverse of 3 is 2, right? Hopefully this is like, right, straightforward, right? If the 0.23 is on f, then the 0.32 is on f inverse, right? That's basically all that we're saying here so far. Okay. All right. Now, what about the derivative of the inverse? Well, what we can say is that f inverse prime of 3 is equal to, well, the theorem above basically says 1 over f prime of 2. okay, which we saw as 1 over, and then the derivative here would be 3/4 x squared plus 1, so it'd be 3/4, and then, what is it, 2 squared plus 1. Right, so it is 1 over, and then when you do all of this, you get 3 plus 1, so it'd be 1 over 4. Okay, so 1/4. All right, so the inverse, so the derivative of the inverse evaluated at 3 is 1/4. Well, what is the derivative of f at 2? Well, so f prime of 2 is equal to, you can plug all of these things in, okay, right? And so what we can see here is basically what this kind of boils down to is that the graph of inverse functions have reciprocal slopes. Okay, maybe some of us knew that already, right? But this is basically a way to quickly evaluate values of inverse functions, derivatives, specific values. That's kind of the format it follows. And we can see in this example that, you know, if I start with f, I know that f of 2 is equal to 3, so that implies that f inverse of 3 is equal to 2, and the derivative of f inverse of 3 is equal to 1/4, and the derivative of f of 2 is equal to 4, right? So they have this sort of reciprocal relationship. Okay. Let's take another example, one that's possibly a little clearer. We'll actually look at a graph and everything here. So let's consider the function f of x equals x squared. Okay, this is a function that everyone has seen, and its inverse, f inverse of x equals square root of x. Okay, we're just taking the positive side. Okay, so let's graph it. Let's just draw a picture so we can kind of see what these look like. All right, so you got your xy axis here. Now x squared kind of comes up like that. Okay, so this is f of x equals x squared. And what happens with the inverse? Well, it kind of goes like this. All right. And so points that are here will map down on the inverse. Okay. All right. Okay, so let's kind of break this down for some example points here. So let's start with f of x equals x squared, and so then f prime of x is equal to 2x. Okay, no problem. F inverse of x is equal to the square root of x, and what is the derivative of f inverse? Well, you can just go through this. This would be like x to the 1/2, and so then it would be 1/2 x to the negative 1/2, and so what you end up with is 1 over 2 square root of x. Looks like that. Okay. All right. So here's our functions. Here's f and f prime. Here's f inverse and f inverse prime. Right, so you got your two pieces. Now, so we know that for f, the points, let's say 1, 1, 2, 4, and 3, 9 are on the graph. All right, so this is just the square. 1 squared is 1, 2 squared is 4, 3 squared is 9. Okay, so then that means that for f inverse, the points, and again, 1, 1 would be there, and then 4, 2 should be on the graph, and also 9, 3. Okay, so these are just common facts. Let's calculate the derivatives here. or sorry, the value of the derivatives. Right, so we would have f prime of 1, just plugging 1 in, and what do we get? 2 times 1 equals 2. F prime of 2, right, we would get 2 times 2 equals 4, and then f prime of 3 would be equal to 2 times 3 equals 6. Oh, sorry about that. Okay, so we've got value of the value of the derivative at 3 different points. What about for f inverse prime? Well, for f inverse prime, we would check f inverse of 1. Sorry, f inverse. Too many subscripts. F inverse prime of 1. Well, that's 1 over 2 times the square root of 1, so that's 1/2. Okay, so that tracks. How about f inverse prime of 4? Okay, now notice here, don't get tricked up here, right? Right, we're plugging these in. Right, we just plugged in the 1 and the 1. Now what about the 2 and the 4? Okay, so f inverse prime of 4, well, that's 1 over 2 times the square root of 4, so that's 1/4. Okay, so that tracks. And then, of course, f inverse prime of 9. Okay, remember, plugging in these guys here. These are the points that are mapped between the inverse and the original function. So f inverse prime of 9 is equal to 1 over 2 times the square root of 9. So 1 over 2 times 3, 1/6. And of course, those track as well, right? So the inverse, the value of the derivative at the inverse and the value of the original function, they have reciprocal, they're reciprocal. That's sort of the relationship. So this is a direct application of basically the fact that what we just talked about on the previous page, f inverse prime of x equals 1 over f prime of f inverse x. Okay, so that's what we're looking at here. Okay, so this is a useful theorem in the world of calculus, right? So f inverse of 1, well, let's take this one, f inverse of 4, right? We plug that in. That's equal to 1 over f prime evaluated at the inverse, right? Now the inverse of 4 is 2, so f prime evaluated at 2, right? That would be what you have there. So this is basically 1/4, isn't it? Okay. All right. Good. So that's kind of the long and short of the inverse functions in general. So usually, inverse functions just are, you can calculate the derivative just like normal, but there is this relationship between the slopes, right? Where basically points that correlate are going to have reciprocal slopes. Okay, now let's shift gears a little bit and talk about some of the trig inverses. So in the trig world, right, we've got sine, right? We've got like sine of x, and its inverse arcsine, right? So there are different ways to denote it. Frequently, it's denoted like this. Right. You may also see, if you recall, arcsine, that notation. Right. So here we are talking about the inverse, the arcsine, not sine raised to the -1 power. Okay. So the question is, what is the derivative of the arcsine? Okay. What's the derivative of the inverse trig functions in general? All right, so here's what it looks like, and we'll just give you the broadest sense, and then we'll prove a couple of these. So let u be a differentiable function of x. Okay, then the following, right? So you've got first the derivative of the arc sine, so d dx of inverse sine of u, right? U is some differentiable function of x. It's equal to u prime over 1 minus u squared square root. Okay, probably didn't see that coming. So we'll get into this in a second. We'll get into it in a second. Let's throw them all up here. What about the cosine, the inverse cosine, d dx of inverse cos of u is equal to negative u prime over 1 minus u squared. Then d dx of the tangent, inverse tangent, the arc tangent, is u prime over 1 plus u squared. Right? So these are like forms, right? These are the forms that they take. Right? U can be anything, any differentiable function of x. So these can have wildly different forms, but given sine and inverse sine of u, arc sine of u, this is the form it takes, right? And so you got to figure out, of course, what u prime is, and you got to square u and plug everything in here. But this is the form that these inverse trig functions have. d dx of arc cotangent, inverse cotangent, that's negative u prime over 1 plus u squared. All right, so you can see there's like a lot of symmetry here. You've got u prime square root of 1 minus u squared, negative u prime 1 square root of 1 minus u squared. That's sine and cosine. Tangent cotangent would be u prime over 1 plus u squared, and then negative u prime over 1 plus u squared. And we'll see for secant and cosecant. That is the sloppiest u ever. So this is the inverse secant of u, the derivative, and it is going to be u prime divided by, now here it's absolute value of u, so the function u itself out front, and then divided by the square root of u squared minus 1. And then 6, the derivative of the cosecant inverse. It's going to look real similar. Negative u prime though, right? Just the negative up top there. All right, so there you go. Those are the those are the derivatives of the inverse trig functions. Now, what the heck does this mean? All right, now how does this work? All right, first of all, what I want to do is show you kind of how you can prove these things. Like, where does this come from? And so what we want to start with is we'll just do a proof of a couple of these. We'll start with the derivative of the inverse sine function. And in the first case, we'll just start with just using x here just to show the method of proof. And then it's very simple to extend it to just general u, right? But let's let y equal the inverse sine of x, okay? Okay, so that's what we'll start with. And we'll prove that this form is kind of what comes out. Okay, so we start with this, and, well, we don't know anything about inverse sine, so let's rewrite this as the sine of y equals x. Okay, now remember, we're interested in dy dx, the derivative with respect to x. So we're going to have to use, what are we going to have to use? We're going to have to use implicit differentiation, which is what we talked about in a previous lecture. Right, so we're going to go d dx of both sides here, like so. Right, we can differentiate this. We know that this is going to be what, cosine of y, and then because we're differentiating y with respect to x, you have to toss on this chain rule piece, dy dx, and then the other side is just 1, right? And so then we can solve this for dy dx, and we get 1 over cosine of y. Okay. All right. And so then what we have to do kind of to get into this form that we want, into this form up here, which in our case would be just 1 over square root of 1 minus whatever 1 minus x squared. To get into that form, we have to recall the Pythagorean identity for sine and cosine. And so the Pythagorean identity says that cosine squared x plus y squared, or plus sine squared x equals 1. All right, so recall that. And so cosine squared x plus sine squared x equals 1, what that implies is that cosine of x would be equal to 1 minus sine squared of x, square root of that whole thing. So let me just write that down here. So cosine of x equals 1 minus sine squared of x, square root. Right? So we want to use that fact here. Okay, and so dy dx equals 1 over cos y, which is the same as 1 over 1 minus sine squared x, square root. All right. And just kind of plugging that value in. And I think it's instructive. Let me go to a new line here. Dy dx equals 1. And it's useful to think of sine squared kind of like in this form sometimes. Right? So instead of, kind of putting the square here, if you put it here, sometimes that's helpful and can help you see things. So if you do it that way, you'll notice that, I'm sorry, these should all be y's. Why did I write it like that? These are y's. Okay, so that's sine squared y. I was using x up here just because, that's, how I wrote this. But, here this is cosine of y. So cosine of y is equal to square root of 1 minus sine squared of y, not x. So it was this typo. This should be a y. Now sine of y, right, we have that up here. Notice this. So sine of y in this expression is the same as x. And so this is just 1 over 1 minus x squared, square root. Okay? And so in this case, this is the u. So in this case, u is equal to x, right? And so u prime is equal to 1. So this is the form, right? If we have d dx of sine of x, then that's going to just be, it's u prime over 1 minus u squared, square root. Well, if u is just x, then this would be 1 over 1 minus x squared. Okay, so we can see that this obviously matches the form in the case of inverse sine. Okay, what about, let's do another one. Let's look at like the tangent, for example. So for it's going to work very similar. For tangent, if you start with y equals the inverse tangent of x, then tangent of y is equal to x. Okay, and we can differentiate both sides. D dx of tan y equals d dx of x. And the derivative of tangent, do we remember that? Maybe it's secant squared, right? Secant squared, right? So it'd be secant squared y. That's the derivative of tangent. And then, of course, dy dx, the chain rule, equals 1. And we can do the similar kind of exercise here where dy dx is equal to 1 over secant squared y. All right, and then here's one where I will be testing your memory. Do you recall the Pythagorean identity for tangent? Well, it looks like this. It looks like it's basically 1 plus tan squared, I'll put theta this time, equals secant squared theta. Okay, So it looks like that. And so here we can see that this guy here can be rewritten like this, 1 over 1 plus tangent squared y, right? And again, I would say it's instructive to just write it like this, 1 plus tan y quantity squared, and then we can see that that's just x, 1 over 1 plus x squared. And again, in this case, the form fits what our theorem showed. So our theorem said that d dx of inverse tangent of u would be u prime over 1 plus u squared. Right? So obviously if u equals x, u prime is 1, and we have the form. Okay, so no problem there. What happens if u is not just something simple like x? Well, let's just see here. I think you'll see that it's very straightforward. So y equals inverse tangent of u, where u here is interpreted as a function of x. Then the tangent of y is equal to u. Differentiate both sides by x. So what do? We'd say d dx of tangent of y equals d dx of u. Okay, so over here we would get the same thing, secant squared y times dy dx equals, now what is d dx of u? Well, that's just du over dx, or you could write u prime because we're going to try to match the notation of our theorem. And so that means we've got dy dx equals u prime over secant squared y. Okay, and just like before, let's just bring this down. Dy dx will equal u prime over, now instead of secant squared y, let's write it as tangent. It'd be tangent squared y plus 1. And we just saw before that's equal to, the u prime stays up top, and this is just going to be u squared. So, right, so same trick. Here's tangent of y, here's tangent squared, so tangent squared is equal to u squared. Okay, there it is. Okay, and that's the form. Now, all of the other theorems sort of follow the same basic approach, the same basic basic technique of deriving the proof. Right, so kind of an interesting sort of derivative, right? It's a derivative where basically you got a form, and depending on what u is, it can look very, very different, but you can differentiate by just kind of pulling the pieces out of the function. Let's do another example, or let's do an example, something concrete here. So y equals the inverse sine of x plus x times the square root of 1 minus x squared. Okay, so here you've got an inverse sine function. Piece of the function is an inverse sine, and then you've got this other piece over here. So let's differentiate this. So y prime is equal to d dx of the inverse sine of x plus d dx of this guy. All right, we can do this. And so this part here, so u here is x, so u prime is 1. Okay, that's for this piece. And so this is really straightforward. We just have to kind of look at the format, and this will end up being 1 over 1 minus x squared. Okay, plus, now we still have this part. All right, now this is going to be the product rule. I'm going to rewrite it though, just because. So this will be x, and then it'll be 1 minus x squared 1/2 power. We're going to use that kind of an approach here. All right, and so the trig piece is out front. And then this guy here will be what? It'll be x times d dx of 1 minus x squared 1/2 power plus, 1 minus x squared to the 1/2 power times d dx of just x. Okay, and so this is all up front here. And the x stays there. Now, how do I differentiate this? Well, I got to use the power rule and then the chain rule, right? So this, I'm going to put a little bracket there. 1/2, and then it's 1 minus x squared to the negative 1/2. And then I got to differentiate the inside, which would be negative 2x. Does that sound right? Looks right to me. Okay, so that's that piece. So this has the chain rule built into it. Plus 1 minus x squared to the 1/2 power times 1. All right. Now this is plus, not equals. Okay. All right, so basically we're done. I mean, it's just a matter of kind of cleaning up. So let's see, 1 over square root of 1 minus x squared. So that's the new piece there. It's kind of the smallest part of this entire problem, but ultimately you would get, like, so here you would get, let's see, this term would be, yeah, so you get a negative 2x squared. I'll just write it, negative 2x squared, and then that's all over 2 times 1 minus x squared to the 1/2 power. And then over here you've got x over, let's see, no, that's not over, so it'd be, oh yeah, sorry, that goes there. There we go. I knew I was missing something. Okay, so the x just applies to this term. Sorry about that. And then this would just be the square root of 1 minus x squared. Okay, and so one more pass and we'll have this one cleaned up. So it's 1 over 1 minus x squared. That's there. And then this we can cancel. So you get negative x squared on top. And 1 minus x squared on the bottom, square root, plus, and then up here you get square root of 1 minus x squared. Okay. Now, all right, so let's see here. I guess we could clean this up a bit more, couldn't we? This is turning into an exercise of just simplification. But if I get a common denominator of 1 minus x squared, then I can do some serious cleanup here. So I've got 1 minus x squared here, and then I got to multiply this like that, right? And that's all over 1 minus x squared. And so I get 1 minus x squared, and then what is this? Well, this is just the same thing, so this just becomes plus 1 minus x squared all over the square root of 1 minus x squared. And what do I get here? I get, so I think I would get what, 2 minus 2x squared over square root of 1 minus x squared. And technically I would write 2, and then that would be 1 minus x squared. Right, looks like that. And then these you can actually do some canceling here, right? Because so this you could just think of as twice the square root of 1 minus x squared squared. Right, it looks kind of like that. And so ultimately you'd be able to cancel this and you'd get 2 times the square root of 1 minus x squared. Okay, so kind of the long ways around, but there you go. So we can see that simplifies down dramatically. Now the whole point of this exercise was really just to see that these can kind of be tossed into the mix here, right? Anytime you have these derivatives, larger derivatives, some portion of it may involve an arc sine or an inverse cotangent or something, and so you can just use those forms like right alongside of your other differentiation rules. Let's try a couple of other examples just really quickly to make sure these are clear. So what about y equals the inverse sine of 2x? Something like that. So in that case, y prime is the derivative of inverse sine of 2x, like that. And, you know, we know that that's just going to have the form of u prime over 1 minus u squared square root. Now, so here we know that u is equal to 2x. So that means u prime is 2. So we can just plug all this in, which almost feels like cheating, doesn't it? But there it is. Okay, so that's the derivative. It almost feels like cheating using these forms, but we went through and we showed where these come from. It's you basically using implicit differentiation and then some really basic trig identities. Okay, let's do one more example at least. Let's try this one, I think. What about y equals the inverse tan of 3x? All right, so again, y prime is equal to, now we know the form for the inverse tangent. It's u prime over 1 plus u squared. Now, you may not ever memorize that, but you know where to find it, right? You know how to interpret it. And so we can quickly see that this is going to be 3 over 1 plus 9x squared. Okay. And how about one more? This one won't be as obvious. So y equals the inverse sine of, or sorry, I want to do secant. Y equals the inverse secant of e to the 2x power. What about this one? So here, u is equal to e to the 2x. What's u prime? Well, that's the one we have to think about, right? Okay, but let's start with this. So dy dx equals, and we know the form is going to be u prime over the absolute value of u times the square root of u squared minus 1. Okay, so u prime we got to think about, but let's plug the rest of this in. So u prime, so then absolute value of u is just e to the 2x, absolute value. And then u squared would be e to the 2x squared, which would be 4x. And then minus 1. So what is u prime? Well, if so the derivative of e to the 2x, right? So this is like the chain rule, right? It's going to be equal to e to the 2x times the derivative of the 2x, right? So u prime equals 2e to the 2x. Okay, so that would mean that we've got 2e to the 2x divided by the absolute value of e to the 2x times the square root of e to the 4x minus 1. And we can definitely do some canceling here, right? So e is always positive, so absolute value of e to the 2x isn't even, absolute value is just the same as the original function. So this is really just 2 over the square root of e to the 4x minus 1. So that's the derivative of this guy. Right? So here's an example where depending on what u is, like the end result can look quite different. So, okay, very good. So that's it for this lecture. And then next time we'll kind of shift gears a little bit and start talking about some of the applications of derivatives and differentiation. So we'll get into some physics problems and some interesting applied problems. So that's it for this one.